Section 10.4, Part 1, Polar Coordinates and Polar Graphs. The polar coordinate system is another way for us to determine points in space. Now, unlike the rectangular coordinate system with x's and y's and an origin, the polar coordinate system is built up of a pole, a directed distance, and a directed angle. So to calculate or find any given point in space in the polar coordinate system, we look at a directed angle that's rotated from what's called the polar axis, about the pole, and then a distance away from that pole to figure out where it is. So instead of going horizontally and vertically, we rotate from the polar axis and again have a certain distance away from the pole. So what we're going to refer to here instead of x and y's is our directed distance we're going to call r, and of course our angle we're going to call theta. And again, that's rotating from that polar axis. So if we look at an example, for instance, plotting these sort of points, we see the different ways we can generate these points in space. So looking at point A, it gives us the ordered pair 3 pi over 2. And again, the first number here is our directed distance. The second value here is the directed angle. So in order to graph or plot, I should say, point A, that means that from the pole here in the center, we want to go out 3, so that's the distance away from it, but at the same time rotate from this polar axis here, which is very similar to the positive x-axis in rectangular. We want to rotate pi over 2 radians. So that places the point up here. So we're going to go ahead, as you can see, we're 3 away, and since pi over 2 is kind of like perpendicular here to the polar axis, that's where we're lying. So we'll label this point A. Now, just like we normally do with angles of revolution, right? If the angle is negative, that means we're just going to go the other way. Clearly, when I made this first one with pi over 2 radians, I was rotating counterclockwise. But with a negative angle, I'm going to rotate clockwise from that polar axis. And in this case, again, the r is 1. So to make point B, we're going to go out 1 and then rotate clockwise, in this case, negative 3 pi over 4. So that would mean if I go out 1 and go that far, put me about right here. And this would be point B. Now for part C, we still have a positive angle, so we'll rotate counterclockwise, but we have a negative directed distance, if you will. Sometimes we call that the radius, if you will, but the directed distance is negative. And that simply means we go the opposite direction. Instead of extending out toward the polar axis, we go the opposite direction. So to plot point C, starting at the polar axis, we'll go back 2, and then from there, rotate 5 pi over 6. Now it's important to remember that once you go back, you're still rotating counterclockwise. So it's just that you're starting over here in that rotation. So we'll go back 2, and then for rotate 5 pi over 6, that's going to take us right about here. So that means point C is going to lie right here. Now, the other thing to point out as we're here is that these points, A, B, and C, certainly were generated by these ordered pairs, but there are many different ways to land on these points. Because these are created by angles of revolution, and obviously we know that coterminal angles can land in the same place, that means that there's literally an infinite number of ways to generate these ordered pairs. All we have to do is, find coterminal angles here. Or we can always switch up how we got there. Instead of going in a positive direction and maybe rotating counterclockwise, we could go in a negative direction and then rotate clockwise. So again, there's many, many different ways of plotting any given point in space with the polar coordinate system. Rectangular coordinates are unique. Polar coordinates are not. Now that we talked about plotting points in space, it's also going to be very important for us to be able to convert between rectangular and polar coordinates. Now the way we're going to do this is we're going to overlay the rectangular system and the polar system and look for relationships that we can use to kind of go back and forth between x's and y's and r's and thetas. So clearly what we're going to do is make a vertical and horizontal axis for our x and y, and the origin and the pole will be in the same place. So when we look at the directed distance here to a point, and this angle right here, that's going to be the polar part of it. However, the horizontal distance from that and vertical distance then would give us the x's and the y's. Okay, so we can either look at this as the pole or the origin depending on our perspective. So what we're looking for is a relationship to maybe go from rectangular to polar or from polar to rectangular. So let's start with going from polar, and we're going to go into rectangular. So what we're going to do is we're going to assume that we know the polar coordinates. We know the r and the theta, and our job is to figure out the x and the y. Okay, so we want to figure out what does x equal and what does y equal. So what I want to do is start with x, right? Because I want to go into rectangular coordinates. We want x values and y values. Now looking at the picture, if I want to solve for x in terms of theta and r, I'm going to be using some right triangle trigonometry, because clearly this makes a right triangle when you look at this, directed distance and of course our horizontal and verticals. So when we look at x and theta and r, the relationship will be the cosine of this angle will equal x being the adjacent side and the directed distance r being the hypotenuse. So I can say right away that the cosine of our directed angle is going to equal x over r. Now obviously my job here is to solve for x, right? So that means if I want to figure out what the x value is at an ordered pair, we'll multiply the directed distance times the cosine of the angle. Now the exact same idea can be done to solve for y. This time obviously in the triangle we'll be looking at the y being the opposite side of the angle, and then of course r still being the hypotenuse. So that means we can say that the sine of our directed angle here is going to equal y divided by the directed distance. So again, solving for y tells me that it will equal r times sine theta. Okay, so obviously if we have polar 1 go to rectangular, this gives us a quick way to calculate the values of x and y. Now on the other side of it, we want to be able to go from rectangular back to polar. So this means looking at the picture, we want to solve for theta in terms of x and y, and then solve for r in terms of x and y. So in this case, we're again, given rectangular, given our x and y's, we're going to polar. So let's begin looking for r. Okay, so if I want to figure out r, and I know the x and the y, the relationship here would be the Pythagorean theorem, because clearly we're looking at the three sides of a right triangle. So the way that we're going to convert here is to say that x squared plus y squared equals r squared. And then if, again, we solve for r, because it's a distance, it's a positive number, so we'll look at it as the square root of x squared plus y squared. Now looking at the angle, to figure this out, obviously looking for, again, a relationship between x, y, and theta. So we'll go back to right triangle trigonometry, and this time to involve only the x and the y, we'll be using tangent, because obviously tangent's opposite over adjacent. So what I know is that the tangent of the angle will equal y divided by x. So if we want to calculate what that angle is going to be, we're going to be looking at applying the inverse tangent or arctangent of y over x. Now it's one important thing to note, however, that if we know x and y, and we use the formula here to solve for it, we have to remember the limitations of employing arctangent. Okay, arctangent obviously only provides solutions in the first and fourth quadrant just by the nature of the function itself. So there may be times when we apply this that the answer we get ends up actually being sort of a reference angle, and we have to realize, knowing where x and y is, maybe there's a different actual angle that takes us there, but obviously what came up in our calculation was simply a reference to that, and you'll see that in a future example. So let's begin trying to just convert coordinates. Okay, so in our first example, let's start with a polar coordinate, and we're going to move this into rectangular. So again, we're going to use the formulas we just talked about. So in this case, to find the x value, right, we're going to take our r and multiply it times the cosine of this angle, right? So that means it's going to be -2 times the cosine of 5 pi over 4. Now, when we come up with this answer, we can simplify as best we can to simply be the square root of 2, because obviously we're multiplying, -2 times, negative radical 2 over 2. But what you have to realize is that some nice points in the polar system don't create nice integer values in the rectangular. So when you kind of overlay those and go back and forth, you're not always going to get nice, really nice points to plot. And that just could go to show you that, the ordered pair that has an x of radical 2 might be easier to plot, especially with a calculator, in polar coordinates. Now let's go ahead and do the y. So again, it's going to be our r value, but this time times the sine of our angle, 5 pi over 4. Okay, and again, we go ahead and multiply that and simplify it. It'll again be the same value, radical 2. And that's just true because obviously at the pi over 4s, sine and cosine are about the same, especially at 5 pi over 4, they're both negative. So this is what it looks like. Now, again, we want to express this as an ordered pair. So while this, of course, is the polar, the rectangular version looks like this. And again, as I said earlier, plotting this might be a little easier to visualize than trying to plot this, as both of these numbers are irrational. Now looking at our second example, we have a rectangular coordinate, in this case it's -3, -3, and we want to make it into a polar coordinate, okay? So this time we have obviously our x and our y, we want r and theta. So to begin with r, remember that's going to be the square root of our x squared plus our y squared. So in this case, it just becomes a square root of 9 plus 9, right? So that's just going to be the square root of 18, which is 3 radical 2. Now to find our angle, remember what we're going to do is we're going to apply the arctangent of the y value over the x value. Now this is going to be a really good example of why solving this out doesn't actually produce our answer. Because when you look at this, this is really just saying what is the arctangent of 1? Obviously negative 3 divided by negative 3 is 1, and that gives us an answer of pi over 4. But the problem though is that if you imagine in the rectangular coordinate system where negative 3 is, that's not going to be where pi over 4 takes us. Obviously, if we go out this far for our directed distance and then rotate this far, this puts us in the first quadrant, if you will, rectangularly. But this is not where this is, right? Negative 3 is in the third quadrant rectangularly. So we have to make sure we're getting all the way around. It's obviously a much bigger angle than pi over 4. So what we got to realize here is that this is actually just our reference angle. And thinking about the rectangular system, we want to be down here. So we have to think, what's the angle over here that references to that? So that means the angle we're actually working with, in this case, would be 5 pi over 4, because that's the angle that references right with pi over 4, but puts us where we need to be over here in the third quadrant. So again, be very careful when you make this calculation, again, just based on the limitations of arctangent, and pay close attention to what the rectangular is needing you to be, right? So sometimes you have to adjust and come up with the angle that makes sense. So when I put this together as an ordered pair, that means that this rectangular ordered pair, negative 3 in polar, is going to be 3 radical 2, 5 pi over 4. Now, in addition to doing ordered pairs and just coordinates, we can also convert equations. Okay, so in our first example here, this is an equation of a graph in polar coordinates. Okay, and we haven't looked a lot about what the graphs look like. We will soon, but this right here is a pretty typical polar equation, right? Usually we solve for r. Now, what we want to do, of course, is to give us maybe an idea what it looks like, or maybe to help us graph it, we want to convert this into rectangular form. So we're going to use the exact same relationships that we used, right, to do ordered pairs, but instead of just getting numerical answers, we'll just have expressions that, instead of being r's and thetas, convert into x's and y's. Now, it's also important to understand that many graphs in polar are not functions. So when you look at the kind of rectangular equations you're going to get, they're not going to always be nice functions. They might be just, implicit expressions with x's and y's on either side. So first off, over here, we want to make some conversions. Now, when I look at it, obviously if I have r, I could replace that with the square root of x squared plus y squared, but over here on the right side, there isn't really a conversion of just cosine theta. But what I do know is that x is equal to r cosine theta. So a really handy thing you can be able to do here is multiply both sides of this by r. Now this side becomes r squared. Not a big deal, because that would just square the square root of x squared plus y squared, so that's not a problem. But over here what it does is I'm going to put it right here next to cosine when I multiply it on the right side, and that gives me a way to convert it to x. So sometimes multiplying both sides by, in this case r, gives us a way to help easily convert into rectangular. So again, r is normally the square root of x squared plus y squared, but r squared then will just be x squared plus y squared, right? The radical goes away. And then over here we have a negative 8, but again, I can replace r cosine theta with x. Now, it kind of depends on your personal preference of how you want to write this. Leaving it like this doesn't tell me a ton. However, if we take the time to do a little bit of algebra, kind of move this over, maybe complete the square, it'll give us a better sense of maybe what this looks like. So what I can do over here is say we have x squared plus 8x, and then we also have a plus y squared, and then over here we have equals 0. But again, as I mentioned a moment ago, if we complete the square, we can do some of that earlier algebra that we did maybe in pre-calculus with different conic sections to give us a better idea of what this polar equation looks like graphically. So if I complete the square, that means what I'm going to do is add 16 over here, since that's half 8 squared, and then of course I'll subtract 16 so I add 16 also to this side. So that means when I factor all this, right, this side over here is going to become x plus 4 squared, okay, and we still have that y squared, and then that equals 16. Now what I've discovered this time is because I have an x squared and a y squared and equals a number, this is a circle, okay, and I know that because obviously there's no denominators on these, so that means it's going to be a nice circular idea. Now obviously with the plus 4, that's just a shift left 4, but this is a circle, radius 4, that's going to be kind of going along the x-axis, moved to the left 4. Now let's go the other way. Okay, so in our second example here, we have a rectangular equation. Again, clearly not a function, I should say, well, not written at one. I think it may be, but we want to convert this into polar. Okay, so again, we're going to use the same relationships as far as converting our x's and y's to r's and thetas. So what I'm going to do first off is take my x and my y and replace both of them with those polar relationships. So I'm going to replace x with r cosine theta and replace y with r sine theta. So that means on the first one, x is going to be r cosine theta, and then replace the y with r sine theta. Now the 4 can just remain a 4, okay? It's really just the x's and y's or r's and thetas in general with equations that we convert. So just like in our previous example, we didn't do anything with the -8, we're not going to do anything really with the 4. Now there's not a lot we can do. However, it is pretty common when you write polar equations to solve for r, so we're going to go ahead and do that. So I do have an r squared, and then what I'm going to do is divide over here by cosine theta and sine theta. Now, I think this is fine to stop. However, if you'd like, you clearly could also express this as r squared equals 4 secant theta cosecant theta, but it really doesn't matter. I think just solving, kind of getting r relatively by itself is a little more common practice with polar equations.